So I'm going to pursue my predating speakers and present a work with Itai Arieli and Rann Smorodinsky. Just sort of as a summary of everything, I'm going to talk about observational learning, or more correctly about Bayesian learning. And to think of an example, let's consider the following situation. There are two possible treatments for a medical condition. One of them is very known and has been around for ages. This is the red pill. And all of a sudden, a new drug has passed the FDA approval process, which is the blue pill. I will try to do a better job at acting than Keanu Reeves, but I want everybody to bear this in mind. So what does it mean that the blue pill has passed the FDA approval process? Basically, it means that it passed some tests on a very small, finite sample of individuals. They know that it's not dangerous. They know that it can cure or affect positively on the medical treatment, but it holds very, very small amount of information as regards to how it compares to existing treatments. Now, the first agent comes along, and this is something that is common to all the work on rational herding, and this is one of the things that drew me to this field. The first agent come along. In our case, it's either a doctor or a patient or some sort of a medical service provider. He reads the FDA report. Maybe he receives a sample from the company, does his own experiment on his own clientele, and he has more information on his clientele than the firms, and he forms an opinion. Let's say the opinion of the first guy is that the traditional treatment is better. What would you do? There is no other information. Let's say that the FDA report is exactly 50-50. He would follow his own signal and go and recommend and endorse the red pill. The second doctor comes along. He has the same conclusion. He also sees the action of the agent who predates him. He also goes to the left, to the red pill. Now here comes the interesting part in this entire literature, in my view. Next time, this Dr. Benson. If he would have come first, he would go and recommend the new pill. But he sees two other smart doctors who chose the other direction. When he does his Bayesian updating or whatever other updating rule there is, I will use Bayesian. He will choose to follow the footsteps of his predecessors. Now, what happens from this point on? Everybody who comes along makes the same decision regardless of his signal, and we have basically a herd. Now, this is problematic because the first two doctors could be wrong. They could be outliers. There's a very high probability of a mistake here. And this is where the traditional literature on social learning pretty much focused on how to find information structures, update rules. You've seen four amazing examples of this line of work. But as an economist who was new to this field, what drew me was the fact that let's look at this scenario for a second. Now, we all live in the real world. What would you do if you were the blue guy? You would offer a discount. You know that if you lose this guy, you will lose the entire history that will follow, the entire future consumers. You will offer a discount to make him, to attract this guy to you, and therefore, by introducing pricing into this simple model, what would you do? You would push back the probability of a herd, which means pricing is a good thing, right? But what happens here? I'm the red guy now. I know that if I capture this Dr. Benson, I will capture the entire history. I will also offer a discount. I will attract him to me. What happens now? I've induced the herd by including pricing. So the introduction of pricing into these models have a very, very significant effect on the governing forces of this entire line of literature. And I'm going to talk a little bit about the governing forces in the existing literature and how we found that pricing alters them. So just to show you that I'm not speaking on something that's completely out of line, there is a very problematic medical condition who affects infants, which is called spinal muscular atrophy. I'm not going to go into this very sad example, but since 2016, Biogen has offered a genetic treatment for this disease, and they were actually first to do that. In less than 2 months ago, a new competitor came, Novartis, and they offered a treatment which is slightly more convenient to the same disease, but it's also very, very expensive. They said that they were going to charge about $4 million per treatment, per one pill, one treatment of this disease. And eventually, when they came into market, they set the price to $2.1 million, which is slightly above the cost of treating of the Biogen's treatment. So pricing definitely took their pricing decision was definitely moved by the competition. What is more interesting is the response. As a response, in the last 2 months, Biogen has been courting healthcare providers and insurance companies in the UK so far, trying to push down the price and keeping the market. Now, as of May, we had less than 7,000 patients who were treated with the original disease, treatment, and only 150 people who were treated with Novartis treatment, which means that if I do a meta-analysis and try to aggregate all existing data, I'm not sure how correct my conclusions will be because I have very, very few data points on Zog and Sama. What happens if this treatment is priced out? We may forego a very good treatment. What happens in other markets where it's not so vivid? How many treatments are going? How many innovations are we losing on the way? And what markets are susceptible to these types of influence? So, to understand a little bit about this and also to summarize this session, let me talk about the classic model of rational herds, which was introduced in the early 90s. We have two states of natures. Either the blue pill is better or the red pill is better. Agents can endorse either the blue pill or the red pill. There is some sort of common prior, which means if I didn't have any additional information, I would read the FDA report and say that the probability that the blue pill is better is mu or half. And each doctor receives some sort of signal as to which of the treatments is better. The signal is drawn from state conditional distributions. What is important to understand about this signal is, the way to look at it is, for example, if I received signal S2 and the prior is half, then this doctor assesses that the blue pill is better, that the state of the world is blue, with a probability 0.7. If he received another signal, if the same doctor received another signal, for example, S1, then the prior probability is 0.2. Now, without any further, and every time the agent sees the actions that come before him, he updates the history using Bayes' law. For example, he can update the probability after seeing red, blue, red, and get some sort of a number. So we can organize all the doctors on a line, ranging from the people who are least confident that the world is blue, the S1 guys, to the people who are most confident that the state is blue, and without any additional information, if the prior probability is half, the guy on the left will recommend red because the probability that the state of the world is red is less than 50%, and the guy on the right would recommend the blue. Now, after they see, let's say, this history, blue, red, blue, blue, they will both do the Bayesian updating. Let's say they reach 0.9, and this time the recommendation will be blue on both sides due to Bayesian updating. Now, in the classical models, the question is, what happens once this happens? We basically don't have any aggregated information anymore, and learning halts. So to be slightly more formal, we know that the process sometimes always converges because it is a martingale, and therefore we say that learning occurs if the limit of the public signal reaches either 0 or 1, it will reach the correct state. And we say that herding occurs if and only if the martingale halted in some interior belief, if the limit is in some interior belief. Now we can, up until now I was talking about two signals, but we can look at continuous or general signal structures, which looks like this. If the state of the world is red, then the signals are drawn based on the orange line. And if the signals are, if the state of the world is blue, then the signals are drawn based on the blue line. And when I'm talking about conformist or least conformist, I'm talking about the two guys in the extremes, being the alpha bar underscore being the guy who is least likely to say that the world is blue. And when I'm talking about alpha bar, I'm talking about the guy who is most likely to say that the world is blue. Now notice that as the prior change, the shifts in these distributions are horizontal, to the left or to the right. So the classical result, which was later called the overturning principle, was that it was by Smith and Sorensen, and they said that if signals are unbounded, what does it mean unbounded? It means that there is always a probability, no matter where the prior is, there is always a probability of having agent with a strong enough signal to overturn the history. So even if the prior belief is 0.99999, there still can be an agent who comes and takes the opposing action. And they state that when prices are fixed, learning occurs if and only if this condition is maintained. Future work tried to challenge it and examine the robustness of this condition on various information structures, utility functions, etc. And it seemed quite robust. Now, what we are doing is we're basically taking the classic model of social learning. We're just adding two firms. We're just adding two firms who declare price simultaneously at each stage. And they're trying to maximize, let's say, for the sake of this talk, the myopic profit. But in the article, we treat more general cases as well. And basically, we say they are competing with each individual customer one by one. Now, I'm telling you, this is our main result. We find a condition where learning occurs and a condition where herding occurs, when signals are bounded and prices are set strategically. Now, this condition is something that we call vanishing margins. To understand what vanishing margins is, you need to look at the lower edges of the distribution. We say that vanishing margins occur when the density around the edge equals 0, when the density of the probability of reaching the most extreme consumer equals 0. So this is this is not vanishing. This is a vanishing margins distribution, and this is a non-vanishing margins information structure. Now, if you want to think about the intuition behind it, we can talk about the consumers who are least conformists. So in marketing, they call them innovators. So basically what we are saying is that if distribution margins are vanishing, then you will have a very small number of innovators. So let me ask you this in the room. Let me open this for a question. I'll have the poll. So we know that learning occurs when signals are unbounded because of the overturning principle. This result holds in the case with pricing as well. But when signals are bounded, we have two options. One of them is that there are many innovators, many people who are nonconformists, and one where there are few innovators, few nonconformists. By show of hands, how many people think that learning will occur when there are a lot of innovators? Okay, how many people think that learning will occur when there are few innovators? Okay, so after consulting with a friend of mine, I've anticipated the results of the poll. The people in the back can collaborate for me. And the poll was that when you have a lot of innovators, you will have learning, and when you have a very small number of innovators, you will see herding. Alas, our results show exactly the opposite occurs, which means if the market contains a large segment of innovative consumers, you will have herding for sure. The distribution will converge to the internal belief. And learning can only happen once you have a very small, very scarce proportion of nonconformist consumers. Now, this is the result. So now, why does this occur? And As you've been through the last hour and a half, you know that the traditional model dynamics is that many nonconformists increase the participation. This is why the intuition of the staggering numbers of 4 people who voted that non-vanishing margins will lead to learning. But what they forgot to count for is the firm incentives. And the firm incentives can be better seen by this graph. So for any price and any prior, we have an indifferent consumer. The people on to the right of this graph will recommend the blue pill. The people to the left of this graph will recommend the opposite. We recommend the red pill. Okay, so if the red pill will decrease the price, it will increase the probability of a purchase from her. It can decrease the price up until the point where it controls the market, which is this point. Because in this way, no matter what state of the world is, the market is basically, the consumer will surely buy from her. Now, the incentives to price so low depends only on the proportion of consumer who lay in the edge. Now, this result we found quite a long time ago, and we were very excited about it. Now, what's really exciting, so the proof has 2 steps. One is to analyze the stage game of the firms, and the other to notice that whenever this deterrence occurs, you will basically have learning, you will have herding, and when deterrence does not occur, you will have herding. Now, Now, this result is very, very nice because it's robust for a lot of extension. I mean, the reason I didn't went through the assumption is that we basically make none as to the farsightedness of the firm, except that they maximize the discounted utility stream. We don't assume anything about the signal structure, except that they are absolutely mutually continuous, which means there is no revealing signal. It also holds for monopolistic firms, and also we show that this is not 0-1 condition, but the smaller the density in the edges is, the higher the informative of the market gets. We are now working on a study. Now, the reason we stopped here in this talk is because we wanted to maintain the structure as wide as possible, similar to what Smith and so on did in their paper. The extensions we're currently working on is having some more structure onto the distribution and information structure and try to speak about convergence speed and how informative our pricing are. So to conclude, we study Bayesian learning, we introduce pricing into the model, and we show that a large proportion of innovation is detrimental to learning. While on the other hand, if you have very few, there is always some sandbox left for experimentation. Sure. So actually what drives this model is the action of the incumbent firm. So the existence of more firms is less crucial. I don't think that this will be difficult to. I think maybe if you talk about the log-likelihood ratio, you need to have some sort of order over the 2 different states, which make the whole analysis problematic. But it's a good question. I didn't think about this as a